Hello, good morning. This is Srinivas Katkuri. I'm the chair of the session, the technical paper session 3A on architecture. So I'm a faculty member at University of South Florida, and it's my pleasure to start this session. And the audience are requested to post their questions on the chat so that the authors can address the questions. So the first paper is entitled Hardware Implementation of Network Interface Architecture for RISC-V based NOC MPSOC framework. Authors are Aparna Nair, Police Manoj Kumar Reddy, Abhijit, Venkatesh Rajgopalan, and Soumya from BITS Pilani, Hyderabad campus. So we'll start with the video of the paper, and I believe after video is played, the authors will be available to take the Q&A.
Hello everyone, myself Aparna Nair MK from Department of EEE, BITS Pilani, Hyderabad campus, India, here to present my conference paper titled Hardware Implementation of Network Interface Architecture for RISC-V based NOC MPSOC framework. My co-authors are Police Manoj Kumar Reddy, Abhijit YL, Venkatesh Rajagopalan, and Soumya J. Here is the outline of my presentation. To start with, I'll just give a brief introduction, followed by research challenges, proposed architecture, experimental results, conclusion, and finally the references. Introduction. RISC-V is a new extensible open source instruction set architecture that has been widely used to support computer architecture research and education. The instruction set specifies 32-bit, 64-bit, and 128-bit address space variants. The ISA implements base integer set instruction set and several other extensions like multiplication, floating point operations, atomic operations, bit manipulation operations, etc. SOC has been introduced to support to satisfy the complexity of modern applications. The communication between the processing elements or cores on the chip is a major challenge in the performance of the system on chip or MPSOC, multiprocessor system on chip. Bus-based communication architecture has been widely used to establish the communication between the processing elements or cores on the chip. But with the advances in the technology, scaling technology, as the number of cores that can be integrated on the chip has increased, the performance of bus-based communication systems started degrading. A router-based interconnection paradigm, that is NOC or network on chip, has been introduced, which can support high bandwidth. NOC follows a packet-based switching technique. To integrate the communicate cores to the NOC router, an interface has been implemented to establish seamless communication between the cores. That is a network interface. Research challenges. While designing an NI to meet the major challenge that we have to meet is meeting the network requirements, especially when the cores are operating at different frequencies. So an NA or a network interface has to be implemented to integrate this RISC-V cores to the NOC router with a lower area and lower power consumption. Validating the proposed design on hardware is another challenge. Here is a block diagram of the NOC router that we have used in our design. We have used a 5-port router. It has 4 global links and 1 local link, which is used to connect the RISC-V core to the NOC router. VC allocator and switch allocator module is used to assign the data from the input link to the output link. We have used a virtual channel router, and the router follows wormhole routing. So the block diagram of the proposed architecture is shown here in this slide. Mainly, the network interface that we have implemented has 2 submodules, which is a fleet maker and packet maker. As I have already mentioned, the router architecture that we are using follows a wormhole routing. So the data communication between the routers take place in the form of a basic flow control unit that is called as a fleet. So the data received from the RISC-V core, which is in the form of packet, has to be converted to the form of a FLIT. So the FLIT maker module in the network interface does this conversion. From the router, when the FLITs reach to the RISC-V core, it has to be converted back to the form of packet. So this conversion will be taking place in the packet maker module. Now, as I have already mentioned, the major challenge that we'll be facing will be the synchronization between the cores and the router. So an asynchronous FIFO has been implemented between the FLIT maker and packet maker module and the RISC-V core to synchronize between the modules. The FIFO that we have used, it's of bit 32-bit and depth 8-bit. In this slide, I'll be giving a brief introduction to the FLIT structure that we have followed in our design. So as I have already mentioned, it's a 32-bit FLIT. There are basically 4 types of FLITs that we have used in our design: header FLIT, payload FLIT, Taylor FLIT, and invalid FLIT. So out of the 32-bit FLIT, the 31st bit it is unused, or it's reserved for future purpose. The next 2 bits, that is 30th and 29th bit, it's used for identifying the type of FLIT, whether it is a header FLIT, payload FLIT, Taylor FLIT, or invalid FLIT. So if it is 0-1, it indicates a header FLIT, 0-0 for payload, 1-0 for Taylor FLIT, and finally 1-1 for invalid FLIT. The next 2 bits, that is 28th and 27th bit, it's used for identifying the virtual channel, which is being occupied by the FLIT during its traversal. So the remaining bits from 27 down to 0, it varies with the type of FLIT. So if it is a header FLIT, the bits from 0 to 7 is used for holding the destination address. 8 to 15 is used for holding the source address. Remaining bits are not used now. In a payload FLIT, the bits from 0 to 27 are used for holding the payload data. And for Taylor FLIT and invalid FLIT, all the bits from 0 to 27 are assigned as 0. So the working principle of our proposed architecture will be explained here. So we have implemented our FLIT maker and packet maker module in the form of a state machine. So to start with FLIT maker module. So FLIT maker module, until a transaction request is received from the core, the FLIT maker module remains in the idle state. So whenever a transaction request is received, either in the form of a write request or a read request, it moves to a header. It moves to the header state. So in the header state, the header FLIT will be formed with the source and destination address that is received from the RISC-V packet. So from header state, in the next clock cycle, the machine will go to the payload state. So from payload state, once all the payload FLITs are made, once the complete packet is from the complete packet, once all the payload FLITs are made, it goes to the Taylor state, and in the Taylor state, the Taylor FLIT will be made. And once the Taylor FLIT will be is made, it goes back to the idle state. So here in the payload state, again we have two more additional states in payload, either payload 1 and payload 2. So why we have used 2 states are there? 2 states means we have used a 32-bit RISC-V core in our design. So since the first 5 bits from 31 down to 27 down to 28, since the first 5 bits are used for either identifying the type of FLIT or identifying the virtual channel, only 27 bits are remaining for our use in the FLIT. But the data received from RISC-V core is of 32-bit. So we have divided the data into 16-bit and 16-bit. So the first 16 bits will be occupied in payload 1, and the remaining 16 bits will be occupied in the payload 2 state. So the payload data that has been received from the RISC-V core will be made into 2 payload FLITs. So once all the payload FLITs are made, we'll be finally making the Taylor FLIT. Now moving to the packet maker, the FLITs that has been received from the router, NOC router, has to be converted back to the packet which can be received by the core. So again, till a valid flit is received from the network, the machine, the packet maker module remains in the idle state. So to indicate whether the flit is a valid or not, we are seeing the 30th and 29th bit of the received flit. So once a valid flit is received, it goes to the header state. By looking into the header flit condition, we are moving to the header state. From the header state, till all the packets are received, the state changes between header to tailor. So what happens here is, from this state, we are retrieving the payload data. Two payload data will be taken, and this payload data, each payload data carries a 16-bit value. 16-bit of the payload will be present in the payload, in each payload flit. So both the 16 bits from the payload data will be taken, and it is combined to form a 32-bit. So till the Taylor flit is received, this process continues. We take the data from the payload flit, we combine the 16 bits of the two adjacent payload data, and we make it as a 32-bit payload. Finally, when Taylor flit is received, it goes back to the packet maker, goes back to the idle state. Now we have compared our proposed architecture with an architecture, existing architecture in the literature. So this is the block diagram for the architecture that we have referred for in our design. So there they have used this NI module, implemented this NI module with some data registers and control registers and some controllers. So here the block which is indicated as CNI controllers does the same function, does the similar function as our packet maker and flit maker module, where a state machine is used and the flits are formed. But in CNI registers include some data bank registers and control registers. So these data bank registers, the size of the data bank register bank, it depends upon the size of the payload in the underlying processing element. And this, they are used for injecting the packets that has to be transmitted. And the control registers, they are used for synchronizing between the transactions that is occurring between the RISC-V core and NOC router. So this particular CNI registers, with they are the data bank registers and controller registers, are being replaced in our design with an asynchronous FIFO. So we could observe that with there are certainly an improvement in the performance of our NI module when we are replacing these registers with a fixed size FIFO. So in the literature work, we could see that the size of these registers depend on the size of the payload data, but here we have used a fixed size FIFO. So in order to do our experiments, so initially we have developed our network interface module. Also the CNI module, which is available in the literature, we have developed it in Verilog HDL and simulated using Xilinx Vivado 2016.2. To do the hardware validation, the implementation is done on ZBoard Sync Evaluation and Development Kit. And for evaluating the performance parameters like area and power consumption, Cadence GNS synthesis solution has been utilized. So here is the experimental results. So we can see that. This experimental results shows the data that has been sent from the processing element 1 or the RISC-V core 1 to RISC-V core 9 on a 3x3 mesh network. So we have used a 3x3 mesh network, and the data that has been sent from the first RISC-V processor and received at the destination RISC-V processor is shown here in the hardware VIO, virtual input output. So the first RISC-V core, it is doing a writing transaction, and second, the destination RISC-V is supposed to do a read transaction. So those two signals are enabled or resetted high, and destination address and source address is given as per the assigned addresses. So we could see that whatever data that we have transferred from the RISC-V core, the same data has been received after transmitting through the NOC router communication network. So again, to validate on this on the hardware platform, the same data has been displayed on the LED of Z-board. So since we have limitations on the number of LEDs on the Z-board evaluation board, only the least significant 8 bits has been displayed here. So we can see that the least significant bits are 78. So here you can see that 0, 1, 1, 1 indicate 7, and 1, 0, 0, 0, 0 indicate 8. So the in order to find the area and performance parameters, we have synthesized the Decide Cadence synthesis solution, and the same NOC router has been used for integrating both CNI and NI, and we could see that our work has shown an improvement of area around 12.78% of area improvement and 6.28% improvement in power consumption. So here is a conclusion. We have implemented a network interface module to interface 32-bit RISC-V core with NOC router. The design has been validated on Z-board hardware platform. The performance parameters of the proposed architecture has been compared with existing architecture in the literature, and we could find that our design has an improvement in the area of around 12.78% and power consumption of around 6.28%. So these are the references that we have used. Thank you.
Thanks for the excellent presentation. There is a question from the audience. What makes this NOC functional only for RISC-V core and not any other ISA base core?
It can be integrated with other cores, but now we are focusing on RISC-V cores. So later on, when we are implementing an application, we are trying to find the suitability for the other cores also, like if there is any other extension to be done or not.
Okay, so in other words, it's not very specific to RISC-V, right? It can be adapted to other.
Correct, it can be adapted.
Okay, so I have one question. So you said like you replace the registers with FIFO, right? Asynchronous FIFO.
Yes.
Like, how did you determine how big the FIFO should be?
Like initially we have considered like we have fixed it to a depth of 8.
Okay.
Like so since the existing literature, since it is the size of the register banks, since it is depending upon the payload size, we have just taken 2 different payload size, but we had just kept the FIFO as our FIFO depth as 8 only, and we have worked for different payload size. So with the size, we could see that when the payload size, even the payload size is increasing, with our fixed size of 8, we could find that there is an improvement in our work.
I see. Because like, won't you run in like an overflow? Like, for example, let's say, like the consumer, you're basically in between and you are getting the flits, right? Yes. And let's say if there are more flits that are going out than coming in, less flits going out. So what will happen? Like, how would you handle such a buffer overflow or like an overflow condition?
Some handshake, like delay has to be given over there. So we have in the router, we have certain signals which can take care of this. Okay.
All right. Okay. Thanks a lot. And thanks for the presentation.
Thank you. Thanks.
So next, the second paper, which is entitled Scalable Hybrid Cache Coherence Using Emerging Links for Chiplet Architectures. The authors are Sriharsha Gade, Mithali Sinha, Madhur Kumar, and Sujay Deb. And they are from ARM Embedded Technologies Private Limited.
Sorry, I would like to just correct something over there.
Sure. Yeah, please go ahead.
Only I am from ARM. The remaining authors are from IIIT Delhi. And
Okay.
I did this work as part of my doctoral thesis when I was in the university. So ARM has nothing to do with this work.
Okay, got it. Okay, thank you. Appreciate it. So we can go ahead and start the presentation, please.
Good morning, everyone. I'm presenting our work, Scalable Hybrid Cache Coherence using emerging links for chiplet architectures. I'm the presenter Sriharsha Gade, along with my other authors, Mithali Sinha, Madhur Kumar, and Sujay Deb. This is a brief outline of the presentation. We'll be first discussing about chiplet architectures and their associated challenges. Then we'll be discussing the motivation for the current work, that is coherence communication and chiplet architectures. Then we will discuss the proposed coherence protocol, Snoopy over directory protocol, implemented using emerging interconnect options. Finally, we'll discuss the experimental results of the proposed work and conclude this work. Firstly, before we go into the proposed protocol, why do we need chiplet architectures? Traditionally, single chip architectures have been implemented using monolithic die architectures, wherein all the functionalities or all the IPs in the system are implemented on a single die. However, as the technology progresses and we move to advanced nodes and the size of the system or the size of the chip increases, the yield from such monolithic die implementations start reducing, thereby increasing the overall manufacturing cost. One of the viable alternatives to overcome the lower yields of monolithic die architectures is through chiplet architectures. Chiplet architectures, by breaking down a single chip into multiple dies of respective functionality, improve the overall yield because of smaller die sizes, thereby improving or decreasing the manufacturing cost of single chip architectures. In addition to improving the yields, chiplet architectures also provide better scalability, as multiple smaller dies can be integrated into a single system, thereby increasing the number of IPs or the number of functionalities or the number of cores integrated into a single system. Furthermore, they are also very suitable and flexible for implementing modular designs where different functionalities can be easily integrated into a single system. Additionally, these different functionalities or different dies can also be implemented using different manufacturing nodes, different vendors, thereby providing a lot of flexibility for implementing future single chip architectures. The advantages provided by such chiplet architectures have already been shown using state-of-the-art systems like AMD Ryzen processors, where a large multi-core system is implemented using multiple small core complexes along with IO dies. And some of these dies are also implemented using different technology nodes. While chiplet architectures provide significant advantages in terms of yield and scalability over monolithic architectures, they also come with their own set of challenges. These challenges primarily can be categorized into system level integration, reliability issues, and communication within the chiplet architecture. The system level integration challenges are primarily pertaining to implementation of standards, particularly when different dies are from different vendors, tool chains for implementing such architectures or evaluating packaging technologies, so on and so forth. And also they require a tight or good knowledge on the side of a system designer regarding package technologies, as the implementation is tightly coupled to manufacturing and packaging technologies. The second issue primarily pertains to reliability, primarily in terms of thermal, mechanical, and power and reliability issues, wherein different dies can have different power requirements, or they might result in power or thermal hotspots impacting the reliability of the chiplet architecture. Finally, communication within a chiplet architecture is quite different from monolithic dies, since different chiplets can be manufactured using different technology nodes, thereby, and also communication between the chiplets is significantly impacted by the inefficient interconnects that are currently available. These interchiplet communications can lead to different challenges like asymmetry in accessing data or asymmetry in memory access latency. or long latencies and long energy when multiple threads are spread across multiple dies in the system. And finally, coherence communication, which is the focus of this work, which requires broadcast traffic to be sent over across all the cores present across different dies, and receiving of acknowledgements from these different memories or different cores across different chiplets. This is the primary focus of the work, the coherence communication in chiplet architectures. Coherence in multi-core systems itself has been facing several challenges, primarily due to the unscalability of the existing conventional protocols like directory and Snoopy protocols. Because these primarily for directory protocols, they require unscalable area overhead as the system size increases or the number of cores in the systems increase. For Snoopy protocols, is a requirement of ordered interconnection support along with high broadcast traffic, which limits its scalability or implementation to very small core counts. Implementation of such protocols in chiplet architectures face several other challenges, primarily first due to the inefficiency of communication itself in chiplet architectures, especially the high latency for data transfers from one chiplet to another chiplet, or asymmetry for memory communication between these different chiplets. The prevalence of high broadcast traffic in coherence communication further complicates these challenges or exacerbates these challenges. In addition to this, if the different dies are from different vendors or different technology nodes, the lack of system level implementation while designing the chiplets might adversely impact the coherence communication protocol or the choice of coherence protocol to be implemented within the chip or across the entire system. As we said, conventional protocols typically face all these challenges in multi-core systems themselves, and implementation of directories either in a single chip or across multiple chips for directory protocols becomes a significant challenge, or the implementation of proper interconnects between different chiplets for Snoopy protocols also becomes a significant challenge. While hierarchical protocol or hybrid protocols, which have been proposed as improvements over existing conventional protocols like directory over directory or hierarchical directory protocols and directory over Snoopy protocols, do improve the coherence performance over existing conventional protocols, they still have limited scalability when it comes to chiplet architectures. So to overcome these challenges, in this work, we propose a novel hybrid hierarchical protocol called Snoopy over directory protocol, which is implemented using emerging interconnect options. This is the overall overview of a chiplet architecture in our Snoopy over directory protocol. Before I go into the implementation or the details of the chiplet architecture itself, we'll first briefly go over to the protocol implementation. In the proposed protocol, each chiplet or the coherence in each chiplet is maintained using directory protocol, and the coherence across different chiplets or between different chiplets in the system is implemented using Snoopy protocol, thereby implementing a global Snoopy with a local directory protocol. One of the primary challenges for implementing Snoopy protocol across long chip distances or across multiple cores has always been the requirement for ordered interconnection. In the proposed work, we overcome this challenge by implementing the Snoopy protocol using emerging interconnect options like wireless communication or optical communication. This is the overall overview of the proposed Snoopy over directory protocol. In this protocol, as we mentioned, the Snoopy protocol uses wireless communication or optical communication, which can effectively implement a broadcast communication with low latency and low energy across long distances in the chip, thereby providing an ordered bus-like interconnection for maintaining coherence across chiplets. Of course, these broadcast capable emerging interconnect options also improve the data communication, thereby providing additional benefits for improving overall communication across the chiplet architecture. For implementing our proposed protocol, there are a few very simple guidelines that needs to be followed, which are non-invasive or does not require significant changes in terms of how each chiplet is designed or implemented. So before we go into the guidelines for such this implementation, I will provide a brief overview of the chiplet architecture. In the proposed protocol, each chiplet can be of its own technology node, ISA architecture, vendor, implementation, and the proposed protocol does not depend on any of the chiplet design metrics except for the minor guidelines which we will be discussing. Thereby, the protocol is easily scalable or implementable across large variety of existing chiplet architectures and also future chiplet architectures. So in each chiplet architecture, there are processing elements and the associate private L1 caches. A single L2 cache is shared across all the cores within the chiplet. This single L2 cache can be either physically banked or implemented as a single physical structure. And a directory structure is implemented within the chiplet for maintaining directory protocol or maintaining coherence within the chiplet. The first guideline for implementing the proposed protocol comes for the implementation of directory structure, wherein the directory structure has to be implemented as a single physical structure within the chiplet so that the global ordering or global coherence can be easily maintained. While this is a current guideline or a restriction in the current work, in future works, this restriction can be overcome by implementing different emerging interconnect transceivers within the architecture. However, within the current scope of the work, the directory has to be implemented as a single physical structure within each chiplet. Each directory within the chiplet is exclusive of each other and maintains coherence only for the cores within the chiplet, thereby reducing the area overhead requirements of the directory protocol. Then at the global level, a single last level L3 cache is shared across all the chiplets. And this L3 cache has to be implemented in such a way that there is a single bank of the L3 cache, a single physical bank is implemented within each processing chiplet in the architecture. And this bank is associated with the corresponding directory structure within the chiplet. This is the second guideline for implementing the proposed protocol. And finally, a emerging wireless interconnect transceiver is integrated with with the combination of the chiplet directory and the L3 cache bank. All these three units combined together form a single unit within each chiplet for maintaining local directory protocol along with global Snoopy protocol. The requirement for a single structure comes from maintaining event ordering and maintaining integrity of the coherence protocol in Snoopy in the global Snoopy protocol. Finally, the directory implementation within the core has a minor modification, wherein the directory entry or the sharer vector is extended by one additional bit, which is used to identify whether a particular cached block is only shared within the core or is private to the core, or it is shared across multiple cores and multiple chiplets. This is the overall implementation of the proposed Snoopy over directory protocol. As we have discussed, each chiplet can be its own architecture and everything. The three guidelines are a single physical chiplet directory, a single logical last level L3 cache implemented using physical banks, wherein each bank, a single bank is present in each chiplet. And finally, each of the banks is integrated with a emerging link transceiver along with a Snoop controller. We also extend the existing directory entry with one additional bit to recognize whether a cached block is shared within the chiplet or across the chiplets. So the primary modifications in terms of the protocol come from recognizing whether a block is shared within the cache or shared within a chiplet or shared across multiple chiplets, which is identified using a single PU block. So the protocol follows existing protocols like MESI, MOSI protocols, which have been widely implemented. with the additional modification as highlighted by the red color in the figure. So whenever a cached, whenever a core requests for a block, first the block is looked for, the L1 cache is probed for the block. If it is a hit, the protocol remains same as existing conventional protocols. If it is a miss, then the request is forwarded to L2 cache. And in the L2 cache, the block is verified in the directory entries. If the block is present, and if the block is shared only within the chiplet, a simple directory lookup is made, and the corresponding owner of the block responds with the data to the requesting cache, which is very similar to existing blocks, and no changes to the directory entry except for the updation of the sharer vector is required. And it operates similarly as any conventional directed protocol. If the block is also missing L2 cache, then the request is broadcasted over the emerging link to all the chiplets. And the broadcasted coherence request is snooped by all the snoop controllers in other chiplets. And if the block is present in any of the chiplets, the corresponding chiplet will respond with the data while also updating the single additional bit, which is the PU bit in the directory entry, to indicate now the block is shared across multiple chiplets. This is how the protocol is implemented and the only additional updates are required is when a cached block is present across multiple chiplets. And since the emerging link acts as a broadcast bus-like architecture, the order in which the requests are made is also the order in which the coherence requests are serviced, thereby maintaining the event ordering within the protocol without any additional requirements. The implementation of the protocol does not depend on what is a protocol within the chiplet, what is the communication implementation, like the frequency of communication and the protocols present within each chiplet, thereby providing a very flexible and modular protocol implementation. So the primary advantages of existing, the Snoopy over protocol or existing protocols, either hybrid, hierarchical, or conventional protocols, is the local directory protocol is implemented only within each chiplet and is only responsible for maintaining coherence within the chiplet. Thereby, the directory requirements are pretty small and are only limited to the cores within the chiplet. Irrespective of the number of chiplets and the number of cores in other chiplets, and the entire the presence of the block in other chiplets is encapsulated using only a single additional bit, thereby requiring very minor modifications to the directory implementation or the directory protocol within the chiplet. At the global level, the protocol is maintained using Snoopy protocol, thereby removing requirements for large directories or global directories, which increase exponentially in size as the system size increases. These are eliminated in our existing protocol, thereby reducing the overhead requirements significantly as compared to existing hierarchical protocols and also conventional protocols. And finally, since the global protocol is not dependent on the communication protocol within the chiplet, there is no need for any system level information or chiplet level information while designing the system, thereby significantly improving the flexibility of the proposed protocol. Finally, the emerging protocol interconnects provide a broadcast based interconnection, ordered interconnection, and where the communication can be completed using low latency and low energy, thereby significantly improving the energy and latency performance of the proposed protocol. So using very simple design guidelines and minor modifications to existing protocols, the proposed Snoopy over directory protocol significantly improves the coherence implementation, its flexibility, and its performance, as can be seen with the experiment results over existing conventional protocols and hierarchical or hybrid protocols. So we have evaluated the proposed protocol using 64, 128, and 256 core chips, x86 cores, with the combination of either 8 chiplets or 16 chiplets. In the scope of this work, each chiplet is uniform in nature. There are equal number of cores. All the cores are of x86, x64 type. while the work is evaluated using such implementation, this is in no way an restriction for implementing the proposed protocol. So finally the caches are implemented using L1 cache, where each L1 cache is 64 KB 4-way cache, and L2 cache is implemented using single MB per each core as a single structure within each chiplet with 8-way caches. And finally the global L3 cache is implemented as 2 MB per each core and multiple and physically banked across all the chiplets. For intra-chip network on chip topology, we have followed mesh topology, and again this is not any restriction for the implementation of proposed protocol. This is only the implementation for the current within the current scope of the current work. And for emerging links for inter-chiplet communication and the global Snoopy protocol, we have used wireless links which have a data rate of 256 gigabits per second with 0.25 picojoules per bit energy consumption, and they are able and each packet is transferred across the entire chip within single system clock cycle. We evaluate the proposed protocol against against two existing protocols. One is a 2-level hierarchical directory protocol where coherence within the chiplet and across the chiplets is maintained using only directory protocol. And the second hybrid protocol is implemented as a directory over Snoopy protocol, where the coherence within the chiplet is implemented using Snoopy protocol, and the global coherence is maintained using directory protocol. And each of the implementations use Moesi states to maintain uniformity across all the protocols. So these are we evaluate the overall efficacy of the proposed protocol in terms of four metrics: coherence traffic, application runtime, overall network energy, and finally area overheads. So the plots show the improvement provided by proposed protocol in terms of coherence traffic as compared to existing protocols of hierarchical directory, 2-level hierarchical directory protocol, and directory over Snoopy protocol. The left side figure shows improvements over hierarchical directory protocol. The right one shows against directory over Snoopy protocol. As can be seen, on an average across different system sizes, the overall coherence traffic is reduced by up to 60% as compared to any of the existing protocols. These improvements primarily come from reduction of multiple directory requests or directory acknowledgements for global communication. All the directory traffic is encapsulated using single broadcast message using Snoopy protocol, thereby reducing the requirements for coherence traffic significantly using the proposed protocol. And also, as we can see, as a number of cores in the system increases, the reduction in coherence traffic is also increased. Next, we evaluate the efficacy of the proposed protocol using application runtime, wherein the overall application, the completion of the application runtime is compared across proposed protocol and the existing protocols. As can be seen, on an average, the overall application runtime is sped up by up to 2.5 times using proposed protocol as compared to 2-level hierarchical directory protocol, and up to 3 times as compared to a directory over Snoopy protocol. Again, as the number of cores increase in the system, the runtime improvements are also increasing, and different chiplets, as a number of chiplets also increase, the runtime improves in any existing system. So this shows the efficacy of the protocol in maintaining coherence performance irrespective of the number of cores or irrespective of the number of chiplets in the system, thereby providing significant improvements in overall application performance. Finally, we evaluate the coherence in terms of network energy, wherein the overall energy for coherence traffic communication is computed for all coherence messages across all three evaluated protocols. As can be seen, as compared with the 2-level hierarchical protocol, the overall network energy for coherence communication is reduced by up to 60%, and on average by up to 58%. And in comparison with directory over Snoopy protocol, the overall network energy is reduced by up to 55% in the directory over Snoopy protocol, thereby showing significant improvements in terms of coherence traffic, application runtime, and network energy as compared to both existing conventional protocols and hybrid protocols, which have been widely implemented in the state of the art systems. So in this work, to conclude this work, finally in this work, we have proposed a novel hybrid protocol with the global Snoopy protocol and local directory protocol for significant coherence performance improvements across chiplet architectures, irrespective of the nature of the chiplets integrated into the system. The implementation of the protocols follows simple guidelines which are non-invasive or not significant, or trivial guidelines which needs to be followed, thereby improving the flexibility of the protocol, and the lack of need for any system level information further improves the modularity of the proposed protocol. Finally, to improve the performance of Snoopy protocol for global communication, the low latency and low energy broadcast capable emerging interconnects are used, thereby providing efficient communication and coherence protocol across all the architectures. And the significant improvements done in various communication metrics show the efficacy of the existing, show the efficacy of the proposed protocol. Thank you.
Thanks for the presentation. So we don't have any questions yet, but meanwhile, I have a couple of questions. So essentially, what you have done is locally you have directory, and then globally you have Snoopy, right? So Snoopy is like broadcast, whereas directory is like a one-on-one, right?
Yes.
Right. So isn't this studied before in the literature?
So most of the primary hybrid coherence protocol which has been implemented is typically directory over Snoopy, because Snoopy typically is very inefficient when the number of cores in the system increases. Anything beyond 8, to the best of my knowledge, has never been implemented using Snoopy protocol. Whereas in our work, we overcome that limitation using a wireless architecture, wireless or any optical architecture at the global level. Primarily also in this case, the difference is that implementing a global directory or any common central lookup storage for implementing directory for chiplet architecture is quite complex. So that's the primary difference between existing hybrid works and our work.
Yeah. So so essentially, you are saying like there is yours is Snoopy over directory, whereas what has been tried is directory over Snoopy, right? Opposite.
Yes.
So, but however, in your comparison, you haven't compared with them, though, right? You compared only hierarchical directly.
The second protocol that we have compared against is a directory over Snoopy protocol, wherein we implemented the Snoopy within the chiplet. Yes.
Okay, so I misunderstood that. Okay, so that's great. So in your results, like there is one benchmark like Radiosity, right, which has less results compared to others. Seem to be like consistent. So Radiosity has like lower gains compared to others, and then the other one, I think Radix, has a higher gains compared to the average. So can you explain why this is the case?
So in our analysis, what we have found out is Radiosity, a significant portion of the requests are going to the main memory. So what is happening is that every time, I mean, a good portion of the requests are always go to the off-chip memory access. So the overall performance is also impacted by the off-chip memory latency. We do not want to separate those two things because other artifacts will come into the overall evaluation. So we want to keep it consistent across all the protocols. Whereas in Radix, most of the communication is happening within the cores. Thereby, our protocol leverage, all the inter-core memory requests can leverage our protocol implementation as compared to existing implementations.
I see. Okay. Yeah, one last question. I don't see any questions, but somehow what you are proposing, Snoopy over directory, seems to be counterintuitive, right? So typically what we do is like we keep most of the traffic like locally, right? So in other words, the The broadcast, you want to keep it at a low, like a small area. And then long distance is you want to do like a point-to-point or unicast. So I am kind of surprised how your results are better than the existing one.
Yeah, so I think it's a combination of two things. Particularly, this is particularly true for chiplet architectures. This is equally applicable to regular monolithic multi-core architectures also. But particularly in chiplet, the issue is that when we are implementing a global directory structure, but an application is using more cores, particularly when the cores are spread across multiple chiplets, the inter-chiplet communication plays a big role. So every time we make a request and we want to have a communication to the central lookup storage, either which is implemented in the separate chiplet or across multiple chiplets, there is a significant impact on the performance. Whereas the broadcast interconnect, which is implemented using either optical or wireless, which have somewhat similar overall performance numbers, except for the actual physical implementation, we are able to send the requests with very low latency across multiple chiplets, which is not the case with existing protocols. So it's a leverage across how the protocol is implemented by using Snoopy across the global level, and also implementing it using a more efficient interconnect architecture. Both are quite important to the overall protocol implementation.
Okay, great. Thanks a lot. Thanks for being here, answering the questions. And thank you and have a nice day. So we'll move on to the third paper entitled Novel Circuit Topology for Configurable EDP, I believe the energy delay product, and then MIPI D5IO. And the authors are actually, the information is a little bit incomplete on the website. So Sunil Kumar, Aruna Kumar, Lakya, Srinivas Murthy, and Sanjeev Basu. I don't have the affiliation information, so maybe so we'll get that from the video presentation. So yeah, we can start the presentation, please.
Hello, good morning, everyone. Today I will be covering this novel circuit architecture for configurable EDP and MIPI D5IO. Myself, Arun Kumar LS, and co-authors for this paper are Sanjeev Basu and Sunil Kumar CR. We are part of Intel Bangalore. So let me get started with the overview for today. So I'll start off with the motivation. Then we will go over the combo PHY overview. Then the combo display PHY details. We'll go maybe some deep dive into the details. Then the results. Then finally we'll have a conclusions and followed by a question and answers. So with that, let me get started. So we, as we know, there are multiple display form factors. So for smartphone, tablets, they have maybe up to 7-inch, and the tablets and above have 7-inch and more. Then there are VR, AR segments, and then we do have the laptops and ultrabooks and other stuff which have a more than 10-inch display. So as most of us know that we do have these small form factors up to 7-inch are supported by MIPI interface, MIPI DSI, and beyond that, these are supported by the EDP. So the idea we had was like, as there could be only one native display, why can't we kind of merge both of them into a single IP? So that's when we started looking. So before we go to that, I want to kind of spend some differences between these interfaces. So the embedded display in terms of EDP 1.5 can support up to 8.1 Gbps, and the salient features are it is having embedded clocking, then it has a sideband dedicated channels for sideband communications, and the major applications are for supporting more than 8-inch of channel. It supports a retina display, and also it supports longer channels, maybe with higher insertion loss. Then coming to the MIPI DSI D5 2.1, which can go up to 4.5 Gbps of data rate, it has a few differences. Instead of a embedded clocking, it is a clock forwarded architecture. and this doesn't have a sideband dedicated channel. So we have a high-speed transmitter for the carrying the display, and the sideband communications happens through the low power TX and RX, which will be which is connected to the same pad. So the major benefits of this MIPI DSI is the cost. These are the cost-effective panels. Then this can go up to 8-inch of channel. Maybe this can support maybe a short channel. So now with that, let me move to the next slide. So now with these features, we wanted to come up with an option where we can club these two IPs into one, which we called a combo display PHY. So our thought was, as there could be only one native display, we can always have only one IP which can be instantiated in any SOC, and that saves a lot of area, BOM cost, and others. So that was the motivation for us to kind of think of a combo PHY solution. So now let's go into more details for the what is combo display PHY. So this block diagram shows the details of how the combo display PHY architecture is. Before we get there, I would like to kind of spend a few minutes on the salient features. So EDP requires 4 high-speed transmitters and a 1 aux sideband communication, which will have both TX and RX, whereas the MIPI would need a 1 differential clock and 4 high-speed data, and the sideband LPTX is connected to the high-speed TX pads. And this can support up to 4.5 Gbps as part of the DeFi 2.1 standards, whereas EDP can support up to 8.1 with the latest. The channel, what each of them would support is different. The EDP can support up to channel loss of 15 dB for EDP, and whereas for MIPI, it typically has short channels and standard channels as per the MIPI spec, which typically goes up to 12 dB in the case of standard channels. So here, the way we architected this combo display PHY was, as in both the cases, as you can see, you would need 5 transmitters and one for a low speed in the case of aux, but in the case of MIPI, it has to be 1 differential clock and 4 data. So we came up with a combo option of having 5 high-speed transmitters, which can be configured into different functionalities depending on the protocol. So for example, in the case of EDP, we had these 4 transmitters like DDI TX0, TX1, TX2, TX3 as the high-speed transmitters, and we had a dedicated maybe the same instantiation which can be configured like an aux. So this was the configuration for EDP. And if you see, the rest of the 4 are supported by the display logic, TX logic, whereas the last one is having a aux logic because it needs to carry a 10 Mbps sideband communication. So whereas we went over the EDP for now, but now moving on to the transmitter, moving on to the MIPI. So we have the same transmitters reconfigured in when we know it's a MIPI protocol. We'll configure this TX0 as a lane 1 MIPI, lane 2, then the middle one, because as it's the clock forwarded, so we want to keep the clock at the center. So the TX2 will be configured as like a clock lane, and then the TX3 and aux can be configured like lane 3 and lane 0. And so this way we could configure the same transmitter into different functionalities, and which can be softly programmed. So now coming from the controller perspective, we have a MIPI DSI controller controlling the MIPI data path, and the display controller controlling the display EDP path. So from a MIPI perspective, there are some low power modes and other things. So we have the MIPI MIPI controller data going through the logic for majorly the low power control functionality. And whereas we do have a common logic in terms of the data path for doing the PSO, the parallel in serial out, we are repurposing the same logic for both MIPI and EDP. And of course, there are some compensation blocks, and then the clock is coming from the PLL sitting outside. Then the clock gets distributed to all this in a match fashion. And then we do have a common logic, basically doing the sideband and other stuff. And we do have an LDO in place because the MIPI protocol requires for LPTX a 1.2 volt. So we are down converting 1.8 to 1.2 volt, which will be powering the low power transmitter. So with that, let me move to the next slide. So going into more details, how the combo display PHY transmitter data path would be is as shown here. So if you come from the controller path, you have a EDP data coming from the display controller and the MIPI data coming from the MIPI controller. And there are some synchronization logic which needs to be implemented for the MIPI, so that gets implemented here. Then the final data comes to this PSO. So this PSO is a parallel in serial out. It converts 10 bits of data into 2 in the case of EDP, because the interface is a 10 bit for EDP, whereas MIPI it is a 8 bit. So it converts. You can configure this MIPI so softly to act like a 10:2 or a 8:2 type of a PSO. And then for a EDP case, we definitely require a FIR. Basically, the equalization is required. Maybe one tap TXLE is there. Then afterwards, if you see this entire path is a common, it's a combo PHY, which is softly configurable as a EDP or MIPI. So the output of the PSO will be going to the serializer. We have a 2:1 serialization inside this block. So the even and odd data gets serialized, maybe get flopped in the serializer flop. Maybe this acts like a boundary flop between the digital and analog. Then we have the data, even and odd data coming, goes to the serializer, and then goes to the pre-driver, and finally to the high-speed driver. So this is on the high-speed data path I went over. So now coming to the power side. So we have a power gate, embedded power gate, for kind of reducing the leakage power of this block. The output of the PG is going to the LDO. It is a 0.85 to 0.4 volt LDO, which will be converting or maybe providing a swing which would be required for this EDP and MIPI modes of operation. And in the non-EDP and MIPI mode, this LDO will be bypassed, and we will be directly feeding from the power gate, which will be directly going to this. So that would be used for the non-native displays like a DisplayPort and HDMI will be using that mode of operation. Then if you look at the final transmitters, you do have the low power transmitter and receiver connected onto the same pad. And that was a major challenge, and maybe we will discuss, because this would be operating to a 1.2 volt signaling, and we need to kind of take care of the EOS protection. Because in a typical standalone MIPI design, this high-speed transmitter would have been designed with a thick gate. But with a thick gate, we could not achieve a higher speed performance, like which is a requirement in EDP. So hence, we had to come up with a stacked, unique design, which I will go over in the next slide. And then for a lane 0 is a special in the case of MIPI, because it needs to carry the receiver data back. So that's why you see the MIPI low power receiver pads also connected onto this. And then all this VCC HV are 1.2 volt. Then coming to the clocking from the PLL, whatever we get a high-speed clock, which will be going through the duty cycle correction, and then duty cycle corrected clock will be going to the serializer in a matched way. So now, before I go to the details of the circuit, so here are the major differences in terms of the specs for EDP and MIPI. So data rates we already talked about. Swing, maybe it supports 280 to 540 in the case of MIPI, and 200 all the way to 400 at step of 50 millivolt for EDP. Then the DC common mode, what we have in the case of D5, it's 150 to 250. That's why we have this LDO, which is the NMOS source follower based LDO, which will be P input, and NMOS source follower based LDO, which will be helping us achieving the DC common mode. Whereas the EDP is AC coupled, and that doesn't care about that. The from a standard spec perspective, the D5 was maybe they were allowing up to 3 picofarad, but EDP, in order to meet the insertion loss and the IMAS requirement, we had to be within 1.1. So hence we went with the stacked thin gate based design. T-coil, it's not a requirement in both. Equalization is required in both D5 and EDP. And then the equalization range is a minus 3.5 to 1 dB in the case of D5, and minus 6 to 1 in the case of EDP. Okay, with that, let me move to the next slide. So going into the details of the high-speed transmitter. So this is the voltage mode driver, and we have, as you can see, here we have a stacked PMOS and stacked NMOS. The main goal of this was, as we have to configure it a lower swing, the PMOSes for swing range of 400 or maybe less than that, PMOSes will not have sufficient overdrive. So hence we rely on the NMOS. Hence we have gone with a Passkit. Maybe in the later design, maybe from a matching perspective, in the first design we went with both matched on both sides. But in the recent design, we have removed this bottom PMOSes because that's not a requirement. Anyways, this gets compensated. So that saves additional pad cap. And if you look at this P bias and N bias, these are used for multiple purposes. The one thing is basically, in order to protect these thin gate devices from electrical overstress voltage, because these EOS limits are typically around 1.05 volt. With a 1.2 volt exposed, all these will go for there would be an electrical overstress issue. So in order to meet that, so we went with the stacked, and these P bias and N biases will be appropriately driven. For example, this NMOS N bias will be driven to a 200 millivolt of a bias when we are operating the LPTX mode, and that way we protect these devices. Then this is a standard voltage mode driver with here swing. We can easily get it through this M by N minus 0.5. I think that formula. So with that, let me move to the next slide. The other two enablers were how do we do the low power transmitter also with a thin gate, and here also we used a stacked thing. The middle ones are kind of connected to the data, and as we need to do a slow ramp, so we have this the driver, this top and the bottom are connected through this bias overdrive circuit to achieve the slow slopes, what is required for our LP mode of operation. And then finally, so maybe if you look at this, the bottom circuit is the slew rate control circuit, which will be driving to this driver. Hence, we are able to adjust the slopes. because the main thing of LPDX as it has to operate at a lower data rate, so we cannot have a high speed slew rates onto the pads. So in order to control that, we went with this bias based slew rate generation control, which will be kind of starving the pre-driver, and in effect it will be controlling our slopes. With that, let me move to the results. So this has gone to silicon in multiple SOCs, and here are the snapshots of the post silicon results with same combo file configured as EDP 8.1 in the case of one application, showing maybe the mid in between. If you can see the eye mask, that's the eye mask, and there is a plenty of margin. Similarly, for the MIPI, if we configured this into the MIPI DSI 4.5 Gbps configuration with 6 dB, and we also see a sufficient eye margin with that. So yeah, I think with that, let me move to the conclusion. So we have the final conclusion. The combo PHY, it met the purpose of supporting the two IPs with the same IP, and it met all the compliance and other things. So the advantage of this is this provides the flexibility to the OEMs and also the SOC to configure the same port on SOC either to EDP or MIPI. So that's a great flexibility. They can decide it in the last minute also. This is saving a good amount of IP area, almost like 27% in the IP area in the case of 10 nanometer process, and that overall pin cost saving is around 10. And then it also helps the SOC to make small form factor designs. With that, let me go over the reference. I think these are the references, and thank you.
All right, thanks for the presentation. And one question I have is like, can you maybe just motivate why you want to really combine these two standards into one interface?
Yeah, so basically we had a few SOCs which were going into multiple segments, and in those SOCs we were having two instantiations of one EDP IP and one MIPI IP, and because we wanted to configure it, so that thought came to us, and then why don't we club it? Maybe because that way we could save the BOM cost. Yeah, that's the motivation.
I see. So not only area, that's what you showed, like 27% savings is really if you have both in parallel and you pick one, versus if they're integrated, you have about 27-30% savings. Okay, great. And another question I have is like, what is the biggest challenge that you faced? I mean, you have explained many different, parts of your architecture. What is the most difficult like challenge when you try to integrate these two?
I think I would say there were two challenges. One was the overall data path, kind of how we could club. I think that was a major challenge because one was a 8-bit interface and the other was a 10-bit interface. And then other major challenge was the electrical overstress issue, which I mentioned, because the MIPI is a high voltage design, so standard implementations will go with a thick gate. And if I have to club with the EDP because that's a high speed one, I cannot afford to have a thick gate. I think these were the two major challenges.
I see. And so you are aware of that ahead and you try to accommodate that. And any surprises, I don't know if you want to share that, but any surprises post fabrication?
Actually, our initial first silicon, we basically the electrical overstress circuitry went through some hiccups, and I think we fixed that, and now I think it is we are all good, and I think it has gone into almost 7 products going solid actually. Okay,
excellent. Yeah, congratulations, and definitely like
I need to apologize. Maybe I had to record in a car because I had to do it at the last minute. I had to apologize for that. Sorry about that.
No, that's okay. No, it was pretty good and very interesting presentation. So thanks a lot, and again, congrats on successful silicon and product introduction to the product line. So thank you.
Yeah, thanks a lot, Srinivas. Nice.
Yeah.
Thanks for the opportunity.
Absolutely. Thank you and have a nice day. So we'll move to the next fourth paper, which is MAPPARAT, a resource-constrained FPGA-based accelerator for sparse dense matrix multiplication. The authors are from PES University, MR Ashutosh, Santosh Krishna, Vishwas Sudarshan, Srinivas Subramanian, and Madhura Purna Pragna. So we'll go ahead with the presentation, please. Thank you.
Hello everyone, my name is Ashutosh Amar. Today I'm going to present MAPPARAT, a resource-constrained FPGA-based accelerator for sparse-dense matrix multiplication. This work was done by myself, Santosh Krishna, Vishwas Sudarshan, Srinivasan Subramanian, under the guidance of Professor Madhura Purna Pragna at Center for Heterogeneous and Intelligent Processing Systems, PES University. In deep learning applications such as Google Assistant, Autopilot, smart devices, there's one common thing in all of these applications, that is matrix multiplication. So in order to accelerate the deep learning applications, we have to accelerate the matrix multiplication itself. Sparse matrices are mainly very frequent in real-world applications such as image processing, networks, graph algorithms, etc. So the desired properties are acceleration of matrix multiplication by avoiding the redundant operations and minimizing the off-chip accesses, which is very energy efficient, and for the resource-constrained devices having less on-chip memory storage. Consider the matrix multiplications of 3x3 dense matrix. In order to get one output value, you have to do 3 multiplications and 2 additions. Finally, in order to get all of the elements of the output matrix for the 3x3 matrix, you have to do totally 27 multiplications and 18 additions. Now let's consider the first matrix to be sparse, which has only 4 number of non-zero elements. In this particular case, in order to get all the elements of the output matrix C, you just have to do 12 multiplications and 3 additions, which is very less compared to that of the dense case. So the reasons to consider sparsity are skipping of extra multiplications, saving of storage space, saving of energy due to less off-chip accesses, which can be seen from this particular table, which has all the operations from arithmetic as well as the data transfer operations. Here you can see the relative cost of energy of 32-bit DRAM off-chip access as compared to that of the 32-bit integer additions, which is of the range of 6400. Hence, it is necessary for to consider the off-chip accesses seriously. Coming to the algorithms, mainly there are 4 ways of doing matrix multiplications. That is inner product algorithm, outer product algorithm, row-wise product, as well as column-wise product. The desired properties among these algorithms are high reuse of data, less partial sum storage, and less number of input accesses for every output value that is obtained. In the inner product algorithm, for every output value of output value of the output matrix, a particular row and a particular row of a first matrix and particular column of the second matrix is chosen, and 6 values in this particular case is required in order to get one output value, and no partial sum storage is required, and the reuse is not present in this particular algorithm. In outer product algorithm, the column of the first matrix and the row of the second matrix is multiplied in order to get a partial matrix. This is done for consecutive columns of the matrix A and consecutive rows of the matrix B in order to get the partial matrices which are accumulated on top of each other, and finally you get the output matrix after the accumulation. In this particular algorithm, for every output value that is obtained, you need to have 2 input values, indicating that this algorithm has highest reuse of both of the matrices, and the partial sum storage required for this particular algorithm is equivalent to the partial matrix itself. Next algorithm is row-wise product algorithm. In this algorithm, the matrix A is traversed row-wise. Each element of a particular row is multiplied with its corresponding rows of the matrix B, and then the accumulation is taken place for the consecutive elements of a particular row in order to get the final output row of the matrix C. This is carried out for every row of the matrix A in order to get every row of the output matrix. In this particular case, 4 input values are needed in order to obtain one output value, and the partial sum storage required for this particular case is equivalent to 1 row worth of partial partial products. And similar to that of the row-wise, in the column-wise product, the columns of the matrix B are traversed element-wise, and based on each element has its own corresponding column of the matrix A with which it gets multiplied in order to get the partial products. The partial products are accumulated column-wise, and finally, in order to obtain the final output column of the output matrix. This is done for each column of the matrix B. And to get one output value, this algorithm takes 4 input values. and the number of and the partial sum storage required for this particular column-wise product is one column worth of partial elements of matrix A, and the elements of the matrix B are reused in this particular case, whereas matrix A is reused in the row-wise product case. In comparison to all of these algorithms, the data reuse is high in terms of outer product, whereas it's moderate in terms of row-wise as well as in column-wise algorithm. But if you see the partial sum storage, it's also high in outer product, and it's again moderate in row-wise and column-wise. Hence, in our implementation, since it's a resource constraint device, we have chosen to experiment on row-wise algorithm as well as column-wise algorithm. Coming to the compression formats, there were five compression formats that we looked into. They are COO format, CSR format, CSC format, run length encoding, and bitmap. And the desired properties were less storage space and mainly ease of doing matrix multiplication. The first format that we looked into was coordinate format or COO. Here there are three arrays, that is value array, row index array, and column index array. Each element which is non-zero in the matrix is given by its row index and column index, which is 0, 0 in this particular case, and the value is 2. And the dimension of this all the three arrays is equal to the number of non-zeros that are present in the matrix. Hence, it is only dependent on number of non-zeros that are present. This is very easy way of addressing the data from the matrix in order to compute the matrix multiplication in sparse case. And in the next format is compressed sparse row, which is also called as CSR. This format has less storage compared to that of the COO if the number of rows is less than the number of non-zeros that are present. And the value index, the value array and column array or column index array are same as that of the COO, but the only difference is that instead of row index array, we have the row pointer array, which points to the first element of every row. So, for example, in this particular case, 2 is the first element of the first row, and that is the 0th element in the value array. Hence, 0 is appended. Next, in the first row, the 1 is the first element in the first row. Hence, the index for the particular value is also 1. Hence, 1 is appended to the row pointer array. Then, in the next row, 5 is the first element. Hence, the corresponding index of the value array of 5 is 3, which is appended to the row pointer array. And the last element of the row pointer array is usually the number of non-zero that is present in the matrix. So the row pointer array totally has the dimension of m plus 1, that is number of rows plus 1. This format requires extra logic in order to decode the index before compute, which was not there in case of COO format. Similar to that of CSR, there is one more format which is compressed sparse column format, or otherwise called as CSC format. This is even this has less storage compared to that of COO format, and even this requires logic to decode the index before the compute. The difference between the CSC format and COO format is that the value array and the row index array are same as that of COO, but instead of column index, we have column pointer array, which points to the first element of each column. The next is run length encoding. This has very less storage compared to COO, CSR, as well as CSC format, and but it has complicated decoder logic in order to retrieve the index before multiplication. So for the particular matrix, value array is same as that of before, but there is one more array which is called a zero array. Zero array has the contents, that is the number of zeros that is present before each non-zero. So before 2, there was 0 zeros, hence you put 0, and before 1, there were 2 zeros, hence you put 2. Similarly, other elements are also filled. The next format that we looked into was bitmap format. Here, the value array is same, but the metadata or the extra data was bitmap, which is a 2-dimensional 1-bit matrix map. Here, each element of the bitmap 2D matrix indicates if the particular value is in the matrix is a non-zero or a 0. If it's a non-zero, it's indicated by 1 bit 1. If it is a 0, then it's indicated by 1 bit 0. Even this has a very complicated decoder logic in order to retrieve the indices. So this is a comparison between the memory required versus the sparsity for all the 5 formats. Here, the black line showcases the dense format or uncompressed format. The bitmap format is better than all other formats from 10% sparsity up till 95% sparsity. Beyond 95% sparsity, the bitmap suffers compared to that of other formats. The run length encoding, as you can see, is better from 40% all the way up till 99.9%. And CSR and CSC are similar because the matrix that was considered in this particular case was a square matrix where number of rows is equal to number of columns. COO is comparable to that of CSR. However, it's slightly higher than CSR or CSC. But the COO format only drops beyond 99.9% sparsity. And coming to the MapRat. What is MapRat? MapRat is a sparse-dense 32-bit floating point matrix multiplier. It is implemented using HDL, and the algorithms that we looked into were row-wise product and column-wise product. The compression format we chose was coordinate format because of the simplicity and not wasting resources for decoder logic, as it involves a lot of resources for other formats. In the row-wise variant, the algorithm used is a row-wise product algorithm, and since the matrix B is accessed frequently, it is kept near the on-chip memory, and it's a dense matrix that is kept in the on-chip. If the dense matrix doesn't fit in the on-chip, then it is broken into chunks, and the computation is done accordingly. Address generation unit, it fetches the proper dense values from the on-chip memory based on the sparse values of the matrix A, and it is a 6-stage multiplier is used to multiply the values, and the adder and register bank does the accumulation part, and it doesn't involve any index matching, since the partial products that were obtained by multiplying the matrix A with the corresponding values of B are dense. So the index matching is not required in this particular case, and the partial products can be accumulated immediately. In the case of column-wise variant, it uses column-wise product algorithm, and since the matrix A is frequently accessed, it's stored in the on-chip near the compute, and based on the dense matrix, the corresponding column is fed into the multiplier in order to multiply, and the partial products that are obtained in this particular case is sparse in nature. Hence, before accumulation, there has to be some sort of index matching that is required in order to add it to the right value, since the nature of the partial products are sparse in nature. So in the sparse partial product accumulation, particularly for the column-based case, it involves irregular accumulation of partial products. Too many comparators and resources are necessary in order for the accumulation, and data dependencies results in the stalling of the multiplications, because you can't go ahead with multiplications if the accumulations are not complete. This limits the performance, and also due to the addressing overheads. So this is one of the methods for sparse partial product accumulation. In this case, the partial product array, which has value as well as the index, is added with the partial products that are present in the array 2 only if the index match. So if the index doesn't match, they don't add, and this involves comparisons of every value to its every partial product with every other partial products. Hence, it involves a lot of comparators, and also it limits the performance. The next method is to convert the sparse partial product into dense partial product using the index data that is present along with the value. The registers are filled with the values using these indices, and then they are added with the then the contents of the registers are added in just like in the dense format. But due to the filling of the registers based on the index of the partial product, this involves utilizing of lot of multiplexers. Hence, even this is also resource this also consumes lot of resources. And the next method that which we have implemented is using the adder tree and a partial BRAM. In this case, the multiplier has its own partial BRAM. So the partial product that is generated is given as an address to the partial BRAM, which will give the previous partial product based on that address, and the adder adds new partial product along with the previous partial products, and the resulted partial product is updated back to the memory of the partial BRAM. This process takes place until a particular column is traversed fully. Once the particular column is traversed fully, all the partial BRAMs are read by the adder tree in order to convert those partial BRAM content into final output values. While the adder tree does the accumulation, the multiplication is stopped. Only once the accumulation is by the adder tree is done, the multiplication is done. Multiplication is resumed for the next set of columns. Coming to the results, for the sparse dense matrix multiplication in case of row wise and column wise, row wise outperforms column wise in all of the cases of frequency, latency, and energy. The performance of MapRat was observed on an FPGAs, and the matrix used was of 560 cross 560 dimension, with the sparse matrix being 97% sparse. The row wise version gave 2.5 speed up and 2.6 energy reduction as compared to that of the column wise case. The reduction in the energy as well as the speed up improvement in the case of row wise is because of the non-existence of sparse partial products accumulation, whereas in column based case you need to take care of the sparse partial product accumulation, which involves extra logic and extra resources. We also looked at varying sparse matrices, varying sparse identical matrices from 30% sparse up till 90% sparse, and we also estimated the sparse dense latencies for the same, as well as sparse matrix multiplication latencies, and we found that from 30% up till 90% sparsity, it is better to do sparse dense matrix multiplication instead of sparse matrix multiplication, and we found that 3.6 speed up was observed for the same. And concluding, MapRat achieved 2.5 speedup and 2.6 energy reduction compared to that of the MapRat Columbus. This is because of the sparse partial product accumulation that is there in case of MapRat Columbus, which is not there in case of MapRat ProVis. For identical sparse matrices, a speedup of 3.6 was observed when sparsity of one of the matrices was neglected and sparse dense matrix multiplication was carried out instead of sparse matrix multiplication when in the sparsity is in the range of 30 to 90% sparsity. So all of the parameters such as algorithm sparsity, compression format, dimensions, and resource constraints, they impact the performance. Hence, the future work involves exploration and analysis tool in order to find the right match between the algorithm, compression format, dimension, and resource constraints. Thank you.
Yeah, thanks for the very good presentation. And actually, we do not have any questions on this paper. And in the interest of the time, we'll move forward to the invited talk. And of course, you can always reach the authors via email, which will be in your final camera proceedings. So we'll move on to the next invited talk. The last one, we have an invited talk entitled Next Generation Deep Learning Accelerators from Hardware to System by Professor Yakun Sophia Shaw. She's an assistant professor in EECS department at UC Berkeley. She was a senior research scientist at NVIDIA, and she got PhD from Harvard in 2016. So let's go ahead with the presentation. By the way, because of the time issues, the late time, the author, the presenter, Professor Shaw, is not here, but please direct the questions to our email address, which is available on the website.
Good morning, good afternoon, good evening to attendees from all over the world. It's great to see you all here. I'm Sophia Shaw. I'm a faculty member here at UC Berkeley. It's my great honor to be here and share with you some of our thoughts in building next generation deep learning accelerators, especially from a more architecture and system oriented perspectives. It is a really exciting time for hardware design across a wide range of applications from mobile all the way to cloud. We're observing a growing demand for more computational power, more compute throughput across a wide range of deployment scenarios. In particular, using machine learning as a driving example, it's really interesting to see the growth of machine learning is actually even surpass the pace of Moore's law, right? We are seeing the machine learning model complexity growing even faster than Moore's law. This is really great news for hardware design, meaning the demand is very strong. You will have good hardware solutions, you will have new ideas to make our system faster and also more energy efficient. There will always be customers. At the same time, if we look at the supply side, unfortunately, we are also observing a slowing supply in compute. Of course, different people have different interpretation of Moore's law, but fundamentally, Moore's law is about the economics of the semiconductor business. Over the past decades, especially when we look at the more advanced technology node, we have been observing that the cost of manufacturing, the cost for every generation of transistors is also growing a lot more expensive. With that, we cannot rely on the traditional technology scaling to get us the compute and throughput improvement without thinking about, especially from a more architecture and system perspective. So it's really interesting. We look at both the demand and supply side, right? We mentioned earlier, we are observing a growing demand for compute where a lot of applications require faster computing platforms. At the same time, we're also observing a slowing supply of computing, especially from manufacturing side. Well, whenever there is a crisis, there's always means opportunities, right? In particular, we mentioned earlier, if we think about not only from the technology scaling point of view, but also from architecture and the system point of view, it's really interesting to see the growing importance of domain-specific accelerators as a potential solution to really bridge the gap between compute, between the demand and the supply. So what do we mean by domain-specific accelerators? Those are basically customized hardware that are designed for a particular domain, right? So you will look at the mobile market, which is really one of the early adopters of domain-specific computing, right? You will look at generations Apple SoC and even more, in particular, looking at the more recent adoptions of M1 Silicon on Apple's MacBook Pro. It's actually really interesting to see a wide range of computing platform, computing IPs actually being adopted on this SoC. Of course, we still see CPUs, GPUs, and also, of course, shared memory as in this kind of SoC. But over years, we have also been observing an increasing number of domain-specific accelerators. Like we discussed earlier, those are specialized hardware that are designed for this particular application. In particular, this Neural Engine here is a good example of domain-specific accelerators for machine learning applications that has been widely adopted, not only in mobile platform, but also in data centers and cloud. So with that, from our perspective of embracing the next generation of domain-specific computing, what we are really excited about is the opportunity to do full stack optimization of domain-specific accelerators, especially in the context of deep learning. Of course, a lot of innovation is really needed in really thinking about how we can improve accelerator design from both performance and efficiency point of view, but also from design productivity point of view. Over the past couple of years, we have been also working on new design tools and novel architecture components for efficient deep learning accelerations. MACNet and the Simba are two examples there in some of our recent work in really thinking about how we can take advantage of technology scaling, especially package level integration, to build novel domain-specific accelerator for deep learning. Well, we're mostly talking about the design side, right? We mentioned, like, if we look at today's SoC, there are a range of different components actually being integrated at the SoC level, right? So at the system level, we are also very interested in really exploring the space of accelerator integration so that we can evaluate and architect a heterogeneous system on chip or system on package with CPUs, GPUs, a shared memory, and a range of different domain-specific accelerators. As an initial step, our ChipYard and Gemini work really shows the potential and the large design and optimization space when it comes to accelerator integration. Moving up the stack, when we actually think about programming those accelerators, right? We also need to map applications onto different domain-specific accelerators we have. As an example, we have also looked at how we can intelligently and also quickly mapping or scheduling deep learning applications onto domain-specific accelerators, especially using what we call constraint optimization-based approach to analyze the design space, the scheduling space of deep learning accelerator. Due to the time constraint, I will mostly focus on some of our more recent work in thinking about accelerator integration and accelerator programming, since both of them are really important when we actually look at domain-specific accelerators from a more system-oriented perspective. With that, let's get started. So when we think about the accelerator, right, we talk about the importance of domain-specific accelerations for those important emerging applications. At the same time, accelerators don't exist in isolation, right? We mentioned earlier, if we look at the past generations of Apple SoC, we have been actually observing a steady increase of the number of accelerators actually being integrated onto the SoC. All of the accelerators need to interact with each other, need to talk to each other, and in a lot of scenarios, they actually need to collaborate with each other to fulfill some different functionalities or tasks. As an example, this is an interesting use case of mobile SoC on Google's Pixel phone. So what Google explored is that when we actually think about different tasks, in this case, we want to record a high resolution video, right? A range of different IP blocks, ISPs, DRAMs, CPUs, GPUs are actually involved in the coordination and collaboration so that we can actually not only store a compressed version of our video, but also actually be able to view the video on our screen. All of those actually require a lot of different IP blocks, talk to each other, share data with each other, and also coordinate and schedule with each other so that we can actually fulfill those functionality. So this is really important at the SoC level because that actually shows a different way of thinking about the accelerators, not only just individual IP block, but really from a full SoC perspective to see how those different components interact with each other. So when we think about full SoC, right, what types of behavior, what type of interaction that we will actually observe? We think about full system visibility, right? In this example, we have as example SoC, we have a couple CPUs, different accelerators here using Gemini to represent different deep learning. It could also be other type of accelerators, right? And then they have some shared memory and also shared interconnect here. So when you think about full system visibility of accelerators, where accelerators and CPUs and shared memory, they all need to interact with each other. So what are the different types of visibilities here? For example, we look at the memory hierarchy, right? So of course, every individual IPs have their own memory block. At the same time, there is also shared memory, right? So whenever there is shared memory and multiple different IPs are actually active at the same time, there's always a lot of interesting questions about how we can actually handle resource contention, how we can actually guarantee cache coherence in this kind of heterogeneous environment. All of this is very important and could be very different from the way we traditionally looking at multi-core system, right? Because now it's a range of different CPUs and accelerators, and they all talk to each other using different way of issuing memory requests. So that's memory hierarchy, right? Of course, there are also other considerations, right? For example, when we actually, a lot of time we focus on accelerators, but of course, there are also the CPU component, right? Where the CPUs are typically responsible for like manipulating, orchestrating different tasks onto different SoCs and making sure all of them can actually operate correctly and also in a performant manner, right? And sometimes we actually run into unaccelerated kernels. We also need to offload them back to SoC. So this is also CPUs. So this is also very important to actually think about the role of CPUs. And we also show page table worker here, how we actually handle virtual memory. All of these are very important when we think about accelerator integration. So motivated by those factors, right? So we actually, well, that's why we built Gemini, which really specialize in thinking about and also providing a full system view of hardware, software co-design for deep learning accelerators. It provides an entire full stack for the programmer so that we can actually put operating system there. We can run end-to-end applications with different levels of API to support users of different programming experiences. We also provide this full SoC view so that we can see the interactions between accelerators and how CPUs, shared memory hierarchy, and also virtual memory management. All of these are actually very important when we actually approach deep learning acceleration. This work is published at DAC last year and also won the Best Paper award from DAC last year. And all the source code, the setup are publicly available. So feel free to give Gemini a try and share your experience. Due to the time limit, I will not go to a lot of details about how Gemini works, but I will want to show an interesting case study we performed actually using Gemini as a full system design space exploration tool. here. So a very common question that we run into, especially at the SOC level, is that if we actually do get actual area budget, right, we could actually allocate that area budget differently, right? We could either actually allocate actual memory, actual SRAM for individual IPs, so each IP has a bigger memory space. We could also allocate that memory to the shared memory. We show like the shared cache, the shared memory system in today's SoC, right? So that could also benefit not only one accelerator, but also a range of other accelerators who also want to access that memory. So when I think about this kind of question, this is actually very important, but also very challenging to answer because it requires a range of different coordinations and interactions of different components. Gemini really facilitates this type of exploration so that we can actually see the impact, the potential impact of different design decisions. So what we realize that is first, it's actually this decision is highly application dependent. If we actually really has a lot of really interested in accelerated convolution-based deep learning applications, that convolution really dominating. Of course, actually having a bigger scratchpad, local scratchpad is actually more beneficial versus either if we're actually more matrix multiply based or actually doing a lot of residual addition. In those cases, having a large scratchpad is local scratchpad is not that useful. So it's very application dependent, right? At the same time, also very SoC configuration dependent. So the earlier result we show is actually for a single core SoC. But if we have actually a dual core SoC where multiple components are actually accessing the memory simultaneously, we see actually a significant improvement. You will actually have a bigger loss level cache, bigger L2, bigger shared memory, right? So that we can actually boost performance across a wide range of applications because it's a lot more resource sensitive. Right, this kind of decision is very application dependent. It's also very SoC configuration dependent, and Gemini is a tool really help designers to navigate this complicated design space with quantitative analysis. So far, we're mostly talking about integration of accelerators. In the remaining time, we'll also briefly touch on what we mean by scheduling of accelerators, right? So here it's really okay, here is the accelerator SoC we have, right? How do we actually map applications onto these accelerators? So we think about the mapping space or the programming space, right, where we map an algorithm to a particular hardware. There's really a large space, right? Different ways of mapping computations and different ways of prediction data across different memory hierarchy. So all of those are actually very important. And this also has been a lot of recent work in actually designing novel algorithms to evaluate different proposals. What we are really interested is whether we can take advantage of the regularities in both deep learning applications and also deep learning hardware. A lot of deep learning applications are very regular, very dense, linear algebra focused. And if we look at the application, hardware, a lot of them are also very regular. We have a spatial architecture with very regular compute unit and memory hierarchy, right? So this really opens up opportunities to leverage these regularities in both application and hardware and to use deterministic constraint solver to actually solve this problem. So motivated by that, we developed COSA and a constraint optimization based scheduler for spatial architecture. So COSA takes a machine learning operator and also the hardware descriptions of spatial architecture, and it actually quickly generates a valid and also performance schedule in one pass without actually doing expensive iterative search. Again, due to time limit, I will not go into the details of the COSA. Our paper published in the ESCA 2021 has more details, but if we actually compare COSA generated schedule with state of art, we actually get more than 2x performance improvement, and also very importantly, almost 2 orders of magnitude faster time to solution because we don't need to do actually iterative search. We can actually find the design deterministically in one shot. So before I conclude, I'd like to thank all my collaborators, especially my students here at Berkeley, who significantly contribute to all the research work that I mentioned earlier. I also want to thank our sponsors for sponsoring our research. With that, just a quick recap. It's an exciting time for domain-specific accelerator design, and in particular, our group approached the domain-specific acceleration from a more full-stack perspective, where we really innovate, not only thinking about designing of individual accelerators, but also how we can better integrate accelerators into the entire SoC or system on package, and how we can actually program accelerators using different heuristics or different optimization-based techniques. With that, I'm going to end my talk here and happy to take any questions you may have. Thank you.